Hi, I'm Josh, and I'm going to show you how to use the property package to estimate marginal treatment effects in randomized or quasi-experimental studies with intact clusters. So, an analyst who's interested in estimating the treatment effect for an individual in a clustered study might have a data frame of individuals that include columns for outcomes, column indicating whether the individual was in the treatment or control condition, columns indicating the cluster to which the individual belongs, or blocks within which the clustered treatment assignment may be considered ignorable, as well as other covariates. The analyst might pass this data frame to LM or GLM and regress the outcome of interest on the assignment indicator and some additional covariates. Under the assumption that the treatment assignment is ignorable, LM will give you an estimate of the marginal causal effect of treatment, but GLM is going to give you an estimate of the effect conditional on the covariates included in the model. And additionally, the estimate may not correspond to an estimand that the analyst actually has particular interest in if the regression doesn't include weights reflecting the probability of assignment. And those can be difficult or confusing to compute because it requires some familiarity with the causal inference literature, and the assignment scheme might be kind of confusing or difficult. So what the property package does is it introduces this function LMITT, ITT being short for intent to treat effect, and it adapts the familiar LM and GLM interface to incorporate study design information and produce estimates of causal estimands that analysts are looking for. So here we have a standard call to LMITT. It might raise a few questions. Why does the right-hand side of the regression formula just have a 1? Why is weights accepting a string rather than a numeric vector? And the reason is this specification argument here. So the specification argument takes this formula that specifies the treatment assignment mechanism. So in this example that I'm using here, the work, family, and health study, it was a blocked cluster randomized trial that was evaluating the effects of the intervention on employees' survey responses. So on the left-hand side of the formula, we have the binary assignment indicator, and on the right-hand side, we have the clustering and blocking variables. So what LMITT does is it uses this formula to extract cluster-level assignment information from the employee-level data frame. And it uses that to first construct the correct employee-level assignment indicators to use in the regression, and also to compute the correct cluster-level assignment probabilities that get piped into the inverse probability weights that correspond with the estimand specified in the weights argument. LMITT also adjusts for covariates using a pre-fitted prognostic model. So given a fitted model object of the outcome on covariates, the property package's cov80j function is going to elicit predictions from that model under assignment to control on the marginal scale. So that's basically saying predict with the type argument equal to response, and if the model included the treatment assignment indicator to improve model fit, it sets that assignment indicator to 0. So then when you pass those predictions to the offset argument, they get subtracted from the original observed outcomes, and you get this difference in differences type estimate. Cov80j also quietly extracts information that improves standard errors. What we see here is that the standard error that's usually associated with difference in differences type estimates severely underestimates the true variability of the linear approximation to this estimator, which is usually used to derive asymptotic standard errors. And this is in a case where the prognostic model has moderately high dimension. On the other hand, the cluster robust standard errors provided by property conservatively estimate this variability, offering suitable inference. So here we're just finishing off with what a summary call looks like when called on an object fit with LMITT. The arguments that are in that summary call are what we find to be sufficient in eliminating the downward bias that's intrinsic to cluster robust standard errors. And you get degrees of freedom that reflect clustering as well. So just to finish off, LMITT, you can also give it a fit LM model if you already estimated a treatment effect. So if you already have an analysis, just call LMITT on it, see how much you like it. Thanks.